right, how's it going, everybody? I've gotten some questions about a MyOpenMath question that is really kind of one of our most important technological computations here. So I am going to walk through how I set up these questions and answer these questions. I am going to do this in Excel. Even if you're using your TI calculator, I still think you'll be able to get a lot of the exact same intuition about your technological usage, even if you're using your TI calculator here. So still the setups for these are going to be the same. So I'm going to walk through this number 12 from the week 8 homework. They give you a bunch of stuff about a meter stick. I've altered my numbers vaguely right here. I'm just calling them sticks instead of meter sticks. We'll go ahead and talk through how we get all of our computations associated with these problems here. I've also added a couple problems that are not in number 12, but that are other places in the homework. And in particular, the very last one is not in number 12 that we'll do here, but it's very specifically one of interest for several topics coming up in the next weeks here. So I buffed out this question a little bit here, a little bit more than is directly just in the math homework question here, but this is good. This is kind of encompassing all of our computational needs for the near future here coming up. So the first thing I want to point out here is that in this number 12 in week 8, the very first thing that they do is they make this note at the top. If for any part below it can't be answered, enter NA. And I want to first identify exactly what it is that they're talking about. I'm going to write out a couple statements here. If you've been reading along in our textbook here, then one of the things that you should have noticed is that this whole idea of looking at a sampling distribution for a sample mean rather than our individual distributions for individuals is that we saw with the central limit theorem that even not normally distributed uh, underlying variables will still have averages, collective averages that are normally distributed. We saw this with the dice in action, right? We saw the uniform distribution form up into a bell-shaped curve, but it took a number of samples to get there, right? When we just rolled 2 dice, 3 dice, 4 dice, 5 dice, we were getting these like triangular distributions, not bell-shaped curves, even though they're both symmetric. To be normally distributed requires that bell shape, not just anything that's symmetric there. So the statements that we should have been kind of gleaning out of the text here is that if the underlying distribution is not normal. And notice right here, they're telling us that the lengths of the sticks are slightly skewed right. We're not symmetric. If we're not symmetric, we couldn't possibly be normal, right? So these are coming from a distribution that's not normally distributed. But what we are going to find is that the distribution of samples that we collect will be normally distributed here. If the underlying distribution is not normal, we need a sample size of at least n equals 30 for the sampling distribution to be normal. If the underlying variable is normally distributed, then all sampling distributions of the sample mean will be normally distributed, meaning we don't have a limit on the number of sample sizes that we need if the original variable is normally distributed. The point here is just to say, when this box here says, let me fix these here real quick. When this box here says, there we go, that this is for any part that cannot be answered, enter NA. This is saying since our underlying distribution of individual sticks is not normally distributed, then we are going to require that we have at least 30 sticks collectively to be able to talk about what we think their average is going to be. Because our distribution of sample averages does not become more normal until about n equals 30. And it's not a hard rule right there. Typically, if you've got like 28 or 29 as your sample size, it's still okay to say, yeah, our sampling distribution is approximately normal. Let's go on to some calculations here. But again, we need a large enough sample size for the central limit theorem to take effect here. So all this is trying to say to us is if we see scenarios where we're trying to talk about a group average when the group is smaller than a size 30, then the central limit theorem doesn't necessarily give us strong enough information to answer that, in which case we'll report NA for our answer here. So let's talk about the information that they do give us right here. They do give us the information that, let me grab these guys here. Oh, come on, Excel, be nicer to me. They do give us some information about the distribution of this thing here. So let's write down what we see. We do see that we've got a mean of 10 centimeters and a standard deviation of 0.5 centimeters. And so what I'm not going to do right here, notice, is I'm not giving the indication that X is normally distributed because it's not. This information is slightly skewed right, says it's not normal. Right? So we're saying here that X is not normally distributed. Right? But we do know its average is 10 centimeters, and we do know its standard deviation is 0.5 centimeters right here of these sticks. So let's answer a couple questions that are associated with this guy then. And by the way, again, I don't know what this, it's not bell-shaped, right? Why is this not, why is this being weird now? Okay. It's letting me write, so we're not normally distributed. No bell-shaped curve yet. Right? If we take a sample of 30 or more things, then we will see that the distribution of samples of that size will be normally distributed. So first question here, what is the probability of finding a stick with a length of more than 10.6 centimeters? And here's exactly our issue. I don't know because I don't know how my values are distributed. All I know is that they're not normal. There's something skewed right. I'm not sure. I don't even know what distribution this thing is going to follow, so I have no way of talking about what its distribution is going to be. So not sure. Don't know how X is distributed. Now, if it were the case that they had told us that X is normally distributed with a mean of 10 centimeters and a standard deviation of 0.5 centimeters, then we could go ahead and compute this value. But in this case, we weren't given a normal distribution that's associated with the underlying variable. So I literally don't know. This could be binomial. This could be uniform. It could be, I don't know what it is. I guess it's not either of those since it's slightly skewed, right? But the point is there's tons of distributions out there. It's not normal, so I'm certainly not going to use a normal distribution calculator to try and determine that probability. We would need more information to answer that. So our next question here, what is the probability of finding a group of 20 sticks with a mean of less than 10.2 centimeters? So notice in this case, we were told that our sample size is 20, and we want to know what is the probability that we would draw a sample of 20 sticks and find that their mean length is less than 10.2 centimeters. So this is how I'm phrasing this problem. Notice we're not asking a probability about an individual stick. We're asking the probability of taking a sample of 20 sticks and finding an average that's less than 10.2. This isn't about individuals anymore. But again, the point here is that n equals 20. We need n equals 30 for the central limit theorem. So we don't know x bar's distribution. Ooh, my writing is out of control here. All right, so again, n equals 20 is insufficient. We're not guaranteed that our distribution of the sample average, x bar, we're not guaranteed that its distribution is normal yet, because this is a little bit too small of a sample size right here. But now let's get into the one, all right, we've done two no computations here. We just said we don't know yet because we don't have enough information. But now what we're being told here is that we're going to find a group of 50 sticks, right? So now we've got a sample size of 50. We're interested in knowing what is the probability that if we take a sample of 50 sticks, that our average will be greater than 10.3. I want to know what is the probability that x bar is going to be greater than 10.3. In this case now, since 50 is greater than 30, I can now say that I think that I know the distribution of x bar. It's going to be normally distributed. It's going to have the same average as our underlying variable of 10. But since we're looking at groups of them at a time, we know that it's much harder for a group of 50 individuals to deviate from the mean than it is for just one individual to deviate for the mean. So we'll always see our standard deviation get smaller and smaller with larger and larger samples. It's harder and harder for big groups to be collectively all weird, right? There's no way that you're going to walk into a crowd of 100 people and it just so happens that all 100 are taller than average. It's very hard for large groups to deviate. They should have small average deviation. And so here I'm going to see that we're going to get our original standard deviation of 0.5, but this is going to be divided by the square root of our sample size, which in this case is 50. And so I'm going to do a little more computation here, and I'll say this is 10, comma, and what am I looking at here? My calculator, 0.5 divided by the square root of 50, and I'm getting 0.0707. So we have a much smaller standard deviation representing the fact that it's much harder for a group to deviate than an individual. So now I can go ahead and use this distribution information with this probability calculation, and we can go into Excel here and make a computation. So I'm going to go ahead and do equals. And very importantly, I guess before I go ahead and do that, get out of here, you stupid thing. Can I move this? Is it going to get mad at me? No, that's pretty nice. Also, very importantly here, I want to draw a picture that's going to go with this guy. Come on, Excel, you could be nicer to me than this. Oh my gosh. I want to draw where this looks like on my bell-shaped curve out here, right? So I should be doing this here. Let's draw my bell-shaped curve. I now know that I'm centered at 10 right here. And by the way, not very bell-shaped. This is like the triangle that I was just saying isn't bell-shaped before, but I'm doing my best here. So I know that I am at an average of 10. I know that my standard deviation is only 0.07. That's really, really small. Notice that 10.3 already seems like it's like 4 standard deviations away from the average here, right? But the point to me, more importantly, rather than even making necessarily a good estimate, is that I know that this 10.3 is up here somewhere, and I'm interested in the probability that we are above that. So what that means to me is I know that I need to flip my probability statement around. I know that Excel only does our less than statements here. So what I really think I want to rephrase this guy as is 1 minus the probability that X bar is less than 10.3. That will say start with all the area, everything shaded, but then chop off all the unshaded stuff to the left, and that will leave us with the shaded region here to the right. So I'm going to go ahead and now throw this calculation into Excel here. I'm going to do equals 1 minus, I'm going to do my norm.dist. It's going to ask me for x. My x value of interest here is the 10.3. That's our cutoff. It's asking me for my mean. That's 10. Standard deviation, 0.0707. It's the standard deviation of our sample distribution. Cumulative, always going to be true in these cases right here. And it's telling us an incredibly small probability, and we knew to expect that because as we kind of eyeballed right here, if you multiply this number by about 4 is where you're going to get the 0.3 that we are above average right there. So this is about 4 standard deviations above average that we were looking for this to be. So we're getting an incredibly small probability out of this, that E negative 0.5 is telling me that this is 0.00. Let's see, I'm moving this decimal over 5 places. That introduces 4 zeros. So 0.00001101. Looks like we're in binary right here. Or I could write this as 0.0011%, maybe right there. A very, very tiny percent chance associated with that event of seeing something that's ultimately about 4 standard deviations away from average out there. And so notice here, 0.3 used to be, oh, my scrolling here is killing me. 0.3 used to, it's because I moved this column right here. 0.3 used to be less than 1 standard deviation away from the mean, and it is now, with a grouping of 50, it's more like 4 standard deviations away from the mean, representing how much more difficult it is for that group to deviate than an individual. So for our next question here, what is the probability of finding a group of 62 sticks with a mean length between 9.9 and 10.1? So on the one hand, you can think of 9.9 and 10.1 as both being very close to average right here. They're both only like a fifth of a standard deviation away for an individual. But when we take groups of 62 sticks at a time, it's going to be really hard for those 62 sticks to break away from being different from that average, that expected value of 10. So I'm kind of expecting this to be like most all groups of 62 are going to be within 9.9 and 10.1 here. So again, I'm seeing that n is 62. Let's see if I can organize my work a little bit smarter to draw some smarter pictures here. We are identifying we are interested in the probability that we have between 9.9 and 10.1 for the value of x bar for our average, for our sample average. We want it to be between 9.9 and 10.1. Because 62 is larger than 30, we do get that the sampling distribution is going to be normal with an average centered at the usual average. And we're going to always start with our individual standard deviation, 0.5, divide by the square root of the sample size, so that the larger the sample size gets, the smaller this overall standard deviation term becomes. And then I'm going to go ahead and say that this is normal with an average of 10. And in this case, again, pop over to my calculator, 0.5 divided by the square root of 62, and I'm getting here 0.0635. 0.0635. So even smaller standard deviation than before. So notice here now, 10.1, that's 0.06 is one standard deviation. So this is like 1 2/3 standard deviations above and below normal. So even let's eyeball this real quick here. 0.6, you'd need about a 0.6 and then another about a 0.06 and then another 0.04. 0.04 is 2/3 of 0.06. So this is about 1 2/3 standard deviations above and below normal. We know that the middle one standard deviation above and below normal is 68%, and that the middle two standard deviations is 95%. We've got 1 2/3, so we're in between those two there. So I'm picturing something like about like an 85% or something like that, 85% maybe in the ballpark of that guy. Between, I guess it's going to be closer to 80. It should be between our 68% and the 95% right there that we're going to end up seeing. What's the probability of finding between those two? So over here, I am picturing for my normal distribution, I am picturing that we're always centered at this average of 10. Here I can see that we've got our slightly smaller standard deviation of the 0.06. I am interested in being at about 9.9 to 10.1, so that's going to put us about here and here. There's 1 2/3 standard deviations in each direction. So to find this area, where the area is equal to our probability, let's slide on over a box here and throw some stuff here into, okay, there we go, that was nice. Throw our computation in here. So what I'm thinking now is we need to think about this as, I'm going to, I guess, write this a little bit different right here, as the probability that x is less than or equal to 10.1 minus the probability that x is less than or equal to 9.9. The reason we're thinking this is because I'm thinking about, I just insert some right here. That do it for me? Give me a little more room. Okay. What I'm picturing here, oh my gosh, this scrolling is about to give me an aneurysm. Just stay in one place. Just fine, lock it right there. What I'm picturing right here is we will first find all of this area. That arrow right there is the probability that we are less than 10.1. We want to subtract off this probability in the tail that we've accumulated that we don't want. That's our probability that x is less than or equal to 9.9. Ooh, and I guess all these x's get hats on them right there. These are all averages. So we want to accumulate all the area to the left of 10.1, but all the area to the left of 10.1 includes this tail that we're not interested in. So we want to subtract off the area that's in this tail. We'll get that with the probability to the left of 9.9. So now let's go to Excel, type this guy in right here. I'm going to do equals norm.dist. My x value of interest is first the 10.1. It's our upper bound. The mean is 10. Standard deviation 0.0635. True, always. Minus norm.dist. Our new value of interest, our other bound, is the 9.9 for the lower bound. Still a mean of 10. Still a standard deviation of 0.0635. Still true here. Remember that we were guessing about 80% or something, 80, 90%, because we're thinking it's between that 68 and the 95 because we're about 1 2/3 standard deviations away. And 88%. Okay, so we got close to that 80, 90 range that we were thinking right there. So I'm seeing 88.47% for this problem that I've set up right here. We eyeballed it pretty good because that's what our empirical rule is for, is to be able to make those estimates that it's between these known values that are out here. So this was a between probability. So we wanted to arrange our answer as being the difference of two different norm dot dists, the upper bound one minus the lower bound one. All right, so cruising on here, last three questions. The next question here. For a random sample of 28 sticks, what mean length would be the 92nd percentile? Now this is, we're flipping this question around right here. Notice that we're no longer asking what's the probability of something happening. We're saying we know the probability. We want to be in the case where 92% are below and 10% are above. What we want to know is what X value makes that happen, right? So here, notice though, we're being given an N of 28. It's less than 30. So X bar, not yet normally distributed. Don't know. So this is our another one. Remember, watch out. If our parent distribution is not normal, we need to have at least 30 in our sample size to know that the distribution of the averages will be normal. Otherwise, it's still going to be something in between the wonky distribution we started with, the normal, which means it's not quite normal yet, which means our curve doesn't look the same, which means our areas aren't the same, which means our probabilities aren't the same, and that's exactly what we're trying to compute here. So here's another one of our NA answers. Since the parent distribution wasn't normal, and since our sample size was less than 30, we cannot compute an answer. If this number was bigger than 30, we'd compute an answer, even though the parent distribution is not normal. If the parent distribution were normal, we'd have no problem going ahead here because any sampling distribution of any size should also be normal if the underlying distribution of the individual also was. But that wasn't our case here. So let's go on to the second to last question here, where we do have a sample size that's large enough to make a computation here. So we're being given that N is 38. And we are being given the outcome probability here. We're at the 92nd percentile. So the 92nd percentile, to me, I'm going to draw my picture kind of first here, is we're saying we know that we're at the location here where this area equals 0.92. Right? This is my shaded region in a sense right there. It's the 92nd percentile. What we don't know is what X value is going to cause that, or I should say what X bar value is going to cause that. We're looking for an average right here. For a random sample of 38 sticks, what length would be in the 92nd percentile? Meaning 92% of all of the groupings of 38 sticks will have an average lower. 8% of all of the groupings of 38 sticks will have an average that is higher right there. So our 92nd percentile for a sample mean. So what I'm thinking to myself here is I can still form my probability statement here. I can still form my normal statement. Maybe we should do this next here. X bar is going to be normally distributed, average of 10. Our standard deviation here is starting at the 0.5. We're dividing by that square root of 38. And that's going to give us our X bar being, okay, X bar is distributed normally, average of 10. Go to my calculator real quick. 0.5 divided by the square root of 38, and I'm getting 0.08111. All right. And so now I'm picturing that we actually know the probability. We just don't know what X is. So I'll call it K or something like that here. But we want to know what X bar, what X value are we at? So that 0.92 is the area to the left. We're asking this question backwards. Normally, I shouldn't say the word normal basically ever unless I'm in the distribution here. In the previous problems, we were given an X bar value. What's the probability of seeing an average of 10.5? 10.5 is the X bar, and we wanted to get the probability out. Here, the probability is our input, and we want to get the X value out. We have inverted the process here. So here's where I know to use my norm.inv that's associated with this guy here. So I'm going to go equals norm dot in, my inverse normal computation here. This is interested in my probability. That's the area to the left, the probability to the left of the area of the location of interest. That's my 0.92. It's looking for the mean, which is 10. It's looking for the standard deviation, 0.08111. Now, before I hit enter, I just want to make a brief little guess here. This is clearly pretty far up here. There's only 8% that's remaining above right here, but we've got a relatively small standard deviation of 0.08. So even if this is like 2 standard deviations above normal right here, that would only put us at like a 0.16 additional on top of the 10. So I don't know, like a 10.15, 10.16, something in that ballpark right there would be something that I would believe for a value right here. And I'm seeing 10.11, okay, a little bit smaller than I was thinking right there, but still in the ballpark of, I guess, what I was anticipating right here. So this would be to say, if you get a average length of your 38 sticks to be 10.11 meters, then you are going, or centimeters, whatever we're measuring in here, right? Then that would be larger than 92% of all of the samples of 38 sticks that we would end up seeing out there. So we did an inverse computation here because we knew the probability, but we didn't know the value that is associated with that probability, the x values of interest there. For the last one that we're going to do is going to be very similar to this, but we're going to be a little bit more dependent on drawing a picture to help us out with this one. So here, for a random sample of 38 sticks, what mean lengths would span the middle 90% of samples? All right, so we again have that n equals 38. I'm going to save a little bit more room right here for my nice picture drawn though. So now what I'm picturing for our last problem here, and this one's a really important one for things that are coming up, by the way, in particular. I added this question. I think there is one like this in the homework, but this is very important for our upcoming topics here. What we need to envision for ourselves is a middle 90%, to where this is 90%. Now, what I know about a normal distribution, which we do get because n is 38, so we're going to be able to say that x bar is distributed, and I'm really getting the same information as here, right? Because that was also 38. So I'm just going to copy this one right here. Oop, I've already got my... Okay, that was strange. The scrolls always make me nervous here. So x is distributed normally with an average of 10, standard deviation of 0.08111. Our numbers didn't change from that guy right there. So what I need to picture here is that since I know it's normal, I know we're centered at 10, what we are interested in is maybe what I'll call x bar lower and x bar upper right there. So an L and a U for our subscripts right there. What I want to know is what's the lower bound and the upper bound for average size for the middle 90% of the groupings of 38 sticks that we draw at a time. So what I need to be able to identify here is how much area is to the left of any of these. And so you should notice here with the middle 90%, that has to mean that there is 5% in each of our tails. All right? I'm taking the remaining 10% and splitting it up symmetrically into my two tails. So I have a 5% tail, a 5% tail, and a middle 90% to make the entire 100%. So we should notice here that x bar sub L, there is 5% of area is to the left. And for x bar sub R, or U, our upper bound, maybe I should just call it left and right bounds, lower and upper bounds. It looks like how much area is to the left of the upper bound? Well, only 5% is above it. So it has to be that 95% is below it. So 95% is to the left of that value of interest right there. So these, oh, I need to scroll a little bit. So these are really my percentages of interest for this problem right here, because these represent the probability to the left of my locations of interest. I'm trying to use probabilities of interest to find locations of interest on my graph here. So we're going to do two different norm inverses right here. We've been given percents. We want to find the x values that go with those percents. So that's our backward situation. We're doing the inverse of our typical computation here. So we want to know a boundary. I want to be able to say some statement like between 9.9 and 10.1 inches is the middle 90% of groupings of 38 sticks or something like that. So we're looking for a lower bound, upper bound. We're going to get two numbers here. So let's go ahead and slide over here and do these two computations that are required to find the two boundaries here. And my first one then is going to be norm.inv. Again, the inverse here. My first probability is the 0.05. This is my left bound right here. My mean is 10, standard deviation 0.08111. That says 9.866, so about 0.14 centimeters shorter than average. And by the way, you should notice right here, I'm going to do here 10 minus C59, 10 minus that guy right there. Got to do my equals in front of this. Since we're symmetric, the other thing that I expect is I expect this difference, how much we are above average, sorry, we did XL, how much we are below average here should be equal to how much above average we are right here. So I am anticipating, my guess for this guy right here is going to be that we're going to get a 10.1334 because that's going to be exactly 10 plus the amount that we deviated from the average. And we're clearly doing a symmetric kind of interval right here. So I'm going to get that symmetry going on. So let's see if that matches and we'll be done here. So norm.inv, I am taking in a probability and spitting out an x. Here my probability is 0.95 because 95% is to the left of our upper bound. Our average is still 10. Our standard deviation is still the 0.08111. My guess was that I'm going to get this 10.1334 because this guy was 0.1334 below average. So this should be 0.1334 above average because we're looking at symmetric bounds about the middle right there. And we do get exactly that 10.1334 like we were anticipating getting right there. So doing these forwards and backwards, right, are given an x, find the probability. That's our norm.dist. Also, given a probability, find the associated x value, find the location on the graph that's associated with that amount of area. We can do our inverse normal computations here. And you guys in your TI calculators will see the like CDF and CDF inverse, CDF norm and inv norm, I believe, are the two that you get out there. But in any event, this last one in particular will be a very important problem for us in the coming sections out here. So be good to be done with this one. So these are all of our computations here. Obviously, I took a little bit longer than I wanted to, as I always do right here. But hopefully, this helps you figure your way through through the things in really this entire homework assignment, not just number 12, but this certainly did hit the answer to everything in number 12 along the way. So I'll wrap it up here. If you guys got any other questions, certainly feel free to hit me up. Have a good one.